Thanks very much for inviting us to the Coventry and Warwickshire local network to give a talk. I know there's a bit of a blurb there, but long story short, I'm a manufacturing engineer by profession. I've been involved with robotics and automation projects over the last couple of years. Now I advise on automated materials handling systems for Jacobs Engineering. Uh, in parallel to that, then I help the IET by chairing the IET Robotics and Mechatronics Technical Network. So just to start off, what I wanted to talk about today was really just give you a 2-minute overview of what the Robotics and Mechatronics Technical Network do. And then we'll get into the guide to implement an industrial robotics with an introduction to that guide, some types and applications, benefits, barriers, business case, implementation, and then a summary of that guide as well. And then we can follow up with some Q&A. So we shouldn't take too long, maybe 40, 45 minutes to get through this guide here. But I know you probably want me to show you something cool like an Asimov or Boston Dynamics humanoid robot breakdancing with stay wires. But I think it's important to talk about the most common applications of industrial robotics and their implementation rather than the aspirations, let's say. So about the Robotics and Mechatronics TN, we have some upcoming events there now. I'm in presenter mode, so I believe if you can control and click on that link there, which will bring you to our NGEX page with the IET. So we have on that page then there's a couple of different events that we have upcoming. So there's a redundant electromechanical actuator for aerospace that's design principles and equalization strategies. So Fawaz Anaz is giving a talk on that next week. Also, we have Lisa Konstantinova attending the International Convention on Robotics and Automation, large international robotics conference, probably the biggest one around. She's going to write a blog on that next month in May. We have Shan Liu, who's organising the London Summer School of Robotics. That'll be around June. On the 4th of June, then we have a talk on soft robotics and cross collaborations. So Rob Skilton is helping with that. And then also in June, we have a talk on cybersecurity and robotics. And then in September, right now, Nick Valentine is organising a talk on autonomous systems. So we have a bit lined up there, and you might be able to browse through it at that link above. I mean, if you want to connect with us, there's a QR code there that you can use, and that'll bring you to the NGEX page. And that'll give you a look at some of our events. You can connect with us online with the same QR code. Also, there's some links there to the Mechatronics page on NGEX. We're also on Twitter, and then we're on LinkedIn there as well. So there's individual links to them if you want. So next, I'll just give you a brief introduction to this guide to implement industrial robotics. It was published last year by Automate UK. The edition was developed as a collaboration between representatives from the Manufacturing Technology Centre, the Irish Manufacturing Research, and Automate UK, and then the IET Robotics and Mechatronics Technical Network. So the guide outlines the various types of industrial robots, the benefits, barriers, and finally the important factors to creating a business case and then implementing the system. So a 2022 McKinsey Global Industrial Robot Survey found that the most common applications of industrial automation are still palletization, materials handling, sorting, and picking. So they're the most typical applications for robots in industry. So it's still very grassroots, down to earth kind of stuff. I'll give you just an overview of the different types and applications of different robots before we get into benefits and barriers. So as far as types goes, first one here is a tricept and hexapod robot. That has the triceps has 3 legs along with a central pillar to hold the head in place, whilst a hexapod uses 6 legs. Uh, these robots are very rigid but offer a limited envelope and orientation, and the robots can be used for machining operations. So in the same attempt, there should be a link there down on this page that you can open up to get the source for that particular picture that's on the screen there. So Cartesian robots slide on an X, Y, Z axis. They have a cuboid envelope of reach and operation. They can be very accurate but are inflexible. These are predominantly used for pick and place operations. They have 3 degrees of freedom, and typical application would be, say, pick and place of printed circuit board components onto a printed circuit board. So Scarrow robots have 4 degrees of freedom. They can be used for assembly and for palletization. They are very accurate at very high speeds, but again, only have 4 degrees of freedom. For jointed arm robots, then, they come in many different configurations and payload capacities, making them very flexible tools for use in automated assembly lines. Their use and configuration can be combined with many other robots mentioned in this deck. It's commonplace to find mounted on mobile robots on a rail track atop a hexapod platform, or even a smaller jointed arm mounted on a larger, all of which are designed with a goal to provide the required manipulation for an assembly task. An example would be welding, hardware fastening, painting, or applying adhesives, as you might do, say, in the automotive industry. Collaborative robots then were first developed by Edward Colgate and Michael Peshkin in 1996. They're commonly referred to now as cobots. They're specifically designed to facilitate safe interactions between humans and robots. Major robotics manufacturers now widely offer these. They have the same degree of freedom and envelope as a jointed arm robot. As long as the part they're manipulating does not pose a risk to humans in the immediate working environment, they do not need a cage around their robot operating area. This is because of a low speed, low payload capacity, and sensors in all motors which will stop operation if resistance to motion is detected. So this allows these robots to operate near human operators. Just move on to mobile robots next. So autonomous mobile robots, AMRs, are likely to rely on simultaneous localization and mapping, so SLAM, for their navigation. Their navigation system utilizes recent advancements in machine vision with light detection and range, intuitive behavior trees, and AI to guide their movements and prioritize tasks based on user inputs. So this adaptive approach allows them to alter their routes in response to obstacles or changing manufacturing needs, enabling efficient movement in unstructured environments. While this navigation method is well developed and stable, it may face challenges in distinguishing routes in areas with a high density of stillage or rack-based legs. So mouse or turtle robots typically drive under a payload, and those payloads can range from hundreds of kilograms to tons. A typical use is logistics. These robots are typically used for in-house transport. They can lower or raise their payload. They could be purchased with frames to help them stage the payload when delivered. And when equipped with a lift, these robots have 3 degrees of freedom and do meet the definition of an industrial robot. These robots usually have 2 lidars for object detection, front and back, and they have very neat kind of turn radiuses, which makes them ideal for small spaces. Tugbots then are more likely to operate in 2 degrees of freedom only. Tugbots, they usually pull carts. They have 1 lidar out front for object detection, as they may not need to operate bidirectionally. As a tug, these robots can tow multiple carts and payloads and can carry tens of tons, so they might be useful, say, in steel manufacture where rolls of steel are being carried around. Forked robots then carry loads that are typically for forklifts or pallet trucks. So basically an adaptation of forklifts. So they're designed to carry shipping pallets, making them suitable for loading and unloading trucks, along with transferring pallets of materials between warehouse and manufacturing locations. As the forks can be raised, these robots have 3 degrees of freedom. So just in terms of benefits then, I mean, the traditional view of industrial robots is that they are only for high volume manufacture. With the advancements discussed though, you can bringing in collaborative robots, mobile solutions, and their integration with more advanced sensors and flexible tooling. This isn't the case anymore. Furthermore, artificial intelligence is a field that could unlock a step change in robotic systems capabilities, particularly in machine vision and in object detection. If this field continues to evolve at a rapid pace. So figure 211 there, it really just shows that the area of application for robots has grown much wider, and these areas for manual or for hard automation have those wedges have grown thinner on this graph of volume versus variety mix. So in the last 12 years, like camera resolutions in particular have improved almost fivefold. Now high-end cameras boast pixel resolutions that facilitate better detection of smaller objects and defects. Improved computer processing powers for vision and for machine learning assists with non-hyperbolic state recognition and allows differentiating false negative reads against an entire picture as opposed to maybe a profile of a small area. So in terms of productivity, robots can work continuously without breaks, leading to higher production rates and increased overall efficiency. They can operate 24/7, reducing downtime, increasing the overall output of manufacturing. They are capable of performing repetitive tasks with high precision and accuracy, reducing the margin for error in manufacturing. This is especially crucial in industries where precision is essential, such as electronics and automotive manufacture. Consistency in production is enhanced as robots perform tasks with a high level of accuracy and repetition, leading to better product quality and fewer defects. Quality control processes can be integrated into the robotic system to identify and address issues early in the manufacturing process. So robotics also facilitates remote operations by allowing monitoring and control from a distance, which can enhance operational flexibility and safety. So in other words, operators don't need to go near something that's dark or dangerous. There's also often a perception that the use of robots leads to job losses. I mean, this has been proven not to be the case, with some studies reaching the conclusion that robots actually lead to creation of other jobs and better jobs, such as one of those publications was the impact of robots on productivity, employment and jobs. And that was published by the International Federation of Robotics, of which BARA would be a member, along with ABB and KUKA and many others. So in both the UK and Europe, there's shortages of labour throughout manufacturing and logistics, and even some trade skills. So robots provide the opportunity to automate the more repetitive tasks, enabling the workers to concentrate on tasks where their capabilities and skills are more required. So typically robots are used for, the dull, dirty, dark and dangerous demanding tasks, allowing workers to be deployed on tasks where their skills are adding value to operation. So the improvements in productivity and competitiveness that result from greater use of robot automation allows the business to pay more for these higher skilled roles. As with the evolution of jobs in information technology, the evolution of robotics will bring about new fields of work and roles, and already has. So by way of example, E&T magazine, published by the IET, they forecast the following new job roles in robotics and automation in the future. So algorithm auditor, already there, empathy consultant, not there yet, health data analyst, automated electric fleet manager, already a job that's in existence, simulation voice user experience, I mean, so much of what we see in AI and machine learning now is about voice to text and voice recognition. And then license order might be another one. So technical risks, I just want to talk about that as well. It's very important to understand that the technical risks involved in implementing automation for a process. So whilst most processes can be automated, there may be significant technical risks in doing so, and carrying out a thorough analysis of the risks involved is imperative, even if the task seems relatively routine. So the assessment of risk is particularly important for complex technical tasks that are often exhibited by the high mix and low volume scenarios that many small to medium sized manufacturers operate in. So in such a scenario, the product design stage will play a large role in determining the feasibility of using robotics to automate the process. To ensure these risks are fully understood and mitigated against, it's recommended that the risks be assessed through the use of tools that help map the process or methods of failure. And those tools might include, say, supplier input, process output charts, or failure mode and effect analysis. And we'll have maybe a quick chat about that later on. In this picture here, figure 2.13, there's an image of light curtains from Keyence, and they're very useful for ensuring that if an operator enters a robot operating area, that it will automatically shut down the robot. So some other barriers: payback period. For organizations, a payback period of 2 years is the norm to be considered. But a well-maintained robot or automation system should be able to provide a minimum of 5 years service, with many systems continuing to operate for 10 years. In terms of health and safety, then, in principle, the use of robotics and automation should achieve like a higher level of safety than manual operations, as they can reduce repetitive strain and other potential sources of injury. Unfortunately, in doing so, they create their own hazards. However, the rate of fatalities and injuries caused by automation systems is very low compared with the rate of arising from human error or deliberate intent to defeat a safety system in place. As such, if designed and installed in accordance with the current regulations and risk assessment methods, robotic and automation systems can improve the working conditions and safety for employees. Sometimes a lack of appropriate skills, both at the implementation and in the use of robots, can cause barriers to the success of the robotic system. Sometimes these skills aren't easily gained, but organizations such as the High Value Manufacturing Catapult, the British Automation and Robotics Association, the Irish Manufacturing Research, and many other research technology organizations and universities are trying to address this by offering courses that embed the appropriate skills into an organization. So I think, for instance, Robot Studio, I know that's being taught in Coventry. That's something that ABB use. That's very useful. So other barriers like floor space. In truth, automation uses more floor space than manual at times. So when you're designing a new robotic system, it's critically important to understand and define the amount of floor space available. So whilst many creative products, applications, and design architectures can be used to fit a great deal of robotics into a given floor space, it can be expensive to change that mid-project. So may also add considerable risk and programming time to the final solution if not properly scoped from the beginning. Sometimes in terms of company culture, there's resistance to change, or fear that robots will steal jobs. And that's often cited as a reason not to install automation. But like we were talking about earlier, there's no real need to fear the use of robotic implementations. In the long term, they have been proven to create new jobs. This fear and general resistance to change can cause significant problems to ensuring effectiveness and implementation of the automation system. So to overcome that, staff involvement in the automation process needs to start very early on, with the need for robotics and what it means for their jobs openly and clearly explained. So that ties in with the Toyota way of automation, where it's human automation that the integration of human activities with automation that's important, and it needs to be human-centric. So while in most cases robots and automation systems are very tolerant to the working conditions they are placed in, you need to consider their environment. So for example, meat processing, agriculture, metal casting, forging, explosive, wet environments, they'll all have unique requirements that must be considered early in the design of a system, as certain precautions will need to be taken. Here we have an image of a robotic system being used in a cheese manufacturer, and that's a Fanuc robot. So final last word on barriers, integration complexity. So integrating robotics into existing production systems can be complex. Compatibility issues with existing machines, production lines, software systems may arise. Achieving a seamless integration often requires specialized knowledge and expertise. The absence of standard practices sometimes poses a challenge for certain companies, hindering their ability to fully harness the potential of emerging technologies or seamlessly integrate novel types of robots into their manufacturing processes. Some organizations have developed proprietary systems and capabilities over time, which they're inclined to maintain. So many clients would say they want to see the best available technology being implemented in their factory that they're going to be using for the next 20 years. But really, it's when it boils down to it, they would prefer to see the best proven technology, and sometimes the best proven technology within their own suite of manufacturing facilities. So in terms of the business case, then you need to ask, what does it cost you now to carry out the existing manual processes? So that could include like manpower, overhead costs, material costs, utilities, training, insurance, revenue impacts due to downtime, the impact of inefficiencies from existing processes, in other words, value added versus non-value added steps, things like staff availability, machine availability, all come into effect there. And also there's a cost of quality. What does it cost to scrap when there's defects? What's the cost of rework? What's the warranty on costs on returned product? Also, what's the cost of the equipment that's being used in your quality inspections to facilitate or to eliminate those defects? So the potential downtime costs as well. In terms of investment costs, like they would include not just the equipment itself, but the effort required. Also to consider is the disruption to normal operations during the installation. Other investment costs to consider is the cost of parts for testing. In other words, the product or the dummy product that you're going to buy to test with the robotic system. Then training needs to be considered, along with changes to upstream or downstream processes that may need for installing the robotic system. So software licensing and integration is an important investment cost that needs to be considered. Other things to consider then are ongoing costs, such as human effort, maintenance, ongoing insurance, and maintenance or spare materials. So it's worth checking if your organization has a preferred approach to return on investment. That's something that's asked for. A return on investment calculation attempts to determine the gain made from an investment to the organization. So a simple ROI calculation is in the form of a gain from investment minus the cost of investment divided by the cost of investment. Factors that may also be considered on the ROI calculation include the cost of money in the future, e.g. interest and inflation, along with long-term costs and returns. So such calculations are often backed up by analysis tools, such as payback calculations, and a graph of one of them is shown in this figure here, showing the cash flow before investment and then the cash flow after investment. And you can see that one overtakes the other about year 3, and that ties in with your payback period then. So in terms of preparing the business case, then really you need to describe the problem you're trying to solve, describe what the automation will do and the expected benefits, describe what it is you want to invest in and why, describe what the financial and other benefits will be, the risks involved, the ROI calculation that we mentioned, and then a high-level implementation plan. So it's important to undertake a structured approach to the implementation of automation solutions, but in many ways, this is not that different to the purchase of any capital equipment. A typical step-by-step approach developed by the Manufacturing Technology Centre, MTC, is shown in figure 220 there. That shows a journey like a tube map, which is generally undertaken step by step to ensure each stage has reached an appropriate level of maturity before moving on to the next step. For example, if the business case cannot be made, it may be necessary to return to the application identification. I'll just point to that there. To modify the tasks to be automated. So you may find yourself going through some strategy loops, some business need assessments, some design for automation to make sure that the solution that's being developed is fit for purpose. So just to describe this a bit more, the automation strategy was in blue there. Would be development of a longer term plan, like 5 years, for the introduction of automation within a business. And that could cover a number of potential applications, not just a single one. It's expected that this would build from relatively simple to more complex applications and include the development of personnel to support this activity as it's undertaken. So there's no point in installing a robotic system if you haven't considered a technician that might be needed to support it. Design for automation then is the loop in orange there. That stage would apply when the business has the opportunity to modify designs or is introducing a new product. This provides the opportunity to consider the automation of the tasks required to produce the product during the design phase. So if you're designing the product itself, being able to consider automation in its design may help quite a lot. So small modifications to the design can make the application of automation much simpler and less costly, and this is to product design. Given the opportunity, it's very worthwhile investing a little bit of effort in design of the product to suit automation. So as much as there's DFX, design for manufacture, design for test, design for procurement, design for assembly, design for automation is also something to consider. The application development then path, that was in green on the last slide. So that relates to those applications where a commercial automation solution is not available off the shelf and some development work is required. In addition to developing a conceptual solution, it's often worthwhile to build a proof of concept to enable the testing and then to validate the proposed solution or design before committing to a full implementation of the concept. So proof of concept, very important there. So just describe some of the steps on the previous slide a little further. So the line walk, that's really the initial survey of the manufacturing facility to gain an objective view of the production floor and begin to identify, analyze improvement opportunities. The business needs assessment is an assessment to consider how well placed the business is to adopt any automation technology and understand how the business will function in its current and future state. Lean processes, it's often worth applying in a lean methodology to ensure business processes are already efficient by removing any non-value added tasks. So that ensures that the automation is applied to the optimum process. There's no advantage to try and automate a process that already isn't working well. And you can reach into your own organizations quite often to do that. So many organizations will have lean champions, people who are Sigma 6 green belts or black belts, and they will be able to help with doing anything from a time and motion study to a value stream map. So we'll talk about that a little bit further in the next slide. Another step that was mentioned on that roadmap, on that tube map, was an application identification. So based on the results of the line walk and the business needs, the most appropriate opportunity for automation adoption can be then identified, and considering any business priorities, concerns, and ambitions. The concept generation step is the development of a high-level ideas on how the automation could potentially be applied to a selected application. So that's a critical one. The user requirements specification then outlines the key functions and performance requirements of the system. And it can also be used to define the service, delivery, assembly, and testing qualification requirements and their performance metrics. Even if it's something like delivering a drawing, you could say that needs to be a drawing, you know. The business case, obviously we talked about that, but that's required to understand the potential value that may be achieved through automation and identifying the application by developing return on investments or rough order magnitude costs of a typical solution. Feasibility assessment involves determining then whether or not the concepts are achievable through existing off-the-shelf products or robotics, and if not, the level of work that would be required to develop and validate a bespoke solution. And if necessary, application development can then be considered. So simulation is also one of the steps there. So, and I'll talk about this a little bit further later on. So the selected concept can be simulated to test the performance and behavior of the system, to provide key insights to the future operation and the potential issues that may arise from the solution. Implementation plan then is the plan to support the implementation of the final solution, which may include assessments of suppliers, equipment trials, training, overall timing plans. So that could be a schedule for implementation. Then the RFQ pack, so that's the request for quotation. And that's bringing together all the information needed for a supplier to quote and build a solution to meet the application. So we'll talk about some of the key elements of that in a few minutes. The supplier shortlist, often called the approved vendor list, the AVL, that needs to be put together and approved within your organization. So credit checks and stuff like that done. So once you've sent out your request for quotation, you'll get the quotations back. You'll carry out a quotation review, which is an appraisal of the proposals received from the potential suppliers. And remember, this isn't just an equipment quote. This will be potentially a design, and there's a technical assessment that's needed on that as well as a commercial assessment. So once that technical assessment and commercial assessment has been done as part of the quotation, then the supplier is selected, and making sure that they're the right supplier for the solution based on their technical abilities and also on the commercial suitability. Once you get to implementation then, working with the awarded supplier to implement the automated system with the manufacturing facilities. And then we move on to operation. So at that point, the automated system should be fully operational within the manufacturing facility. And after operation, then you can assess and continuously assess system performance before moving on to continuous improvement. So once the solution's finally embedded, delivering the expected performance and achieving the desired benefits, then the user may seek further opportunities to automate other processes in line with their automation strategy, which was the 5-year plan we talked about earlier on. So just going back to lean processes again, like I said, often organizations will have lean experts within like Six Sigma green belts and black belts. So often you'd use like a process block flow diagram, things like, which is shown here over on the left-hand side. Other tools that they might use would be a Pareto diagram of defects and the causes of those defects, which sum up to 80% of. So what you can do is, using this Pareto analysis, then you can identify the defects that are causing 80% of your problems and focus on them first in a structured way. We mentioned the supplier inputs, process and outputs tables. Also, you can use cause and effect fishbone or Ishikawa diagrams. The problem being over here on the right hand side, and the different causes being mapped out on the fishbone itself. Failure mode and effect analysis we talked about, that's really just a risk table quantifying the rate of occurrence, severity of occurrence, and the ability to detect that, and giving that a score, that rating a score out of 100. And finally, then other tools that could be used is the value stream map. So showing the amount of inventory at each step in the process, the uptime basically, and then the value added time versus the non-value added time. In other words, waiting. So, I mean, this one slide is probably an entire separate presentation if need be, but I think the key message there is just if you have lean experts within your organization, reach out to them and get their help in assessing the process. Also, I just want to talk a bit more about simulation tools. So we said that was once we get the selected concept, it can be simulated to test the performance. So some tools, discrete event process modeling tools or simulation tools include things like FlexSim, JamSim, which is free, or Witness from Lanner. And here is a very basic attempt at a JamSim model. You can see it's just a basic flow diagram, parts going in, you're generating the parts, machining the parts, inspecting, past inspection, statistics before you ship out, and you can graph them then, showing the number of parts going through at a time, number of defects or whatever. Very easy to set up and gives you a very quick idea of things like throughputs, capacities, and so on. Another one I mentioned there was FlexSim. I'll just see if I can play this. I don't know if I can. Yeah, so here we go. So I'm just going to pause that there because I don't know if you can actually hear the audio that's coming across there. But what's great about FlexSim is that it provides a 3D environment, and that allows developers and clients to visualize the system physically. And you can incorporate that. It's now an Autodesk product, so you can incorporate it with drawing files. You can incorporate it with 3D models such as Revit files, and incorporate them into the model. And like I said, helps clients visualize how material maybe is moving from the ground floor to level 1 before it's picked up by, for instance, an autonomous mobile robot and brought to another production room. So also RobotDK is a great library of fixed arm robots and equipment typical to a robotic station. So you can draw the paths for the robotic arms as opposed to inputting coordinates. And then you can visualize that with a fully 3D visualization tool. So a very useful tool. And this is what's I think important about this is that it's kind of agnostic of vendor. Quite often tools that we would use would be tied to a particular manufacturer or robot vendor. This multiple libraries are there with multiple vendors, and it gives you a very quick indication of whether a particular robotic arm is suitable for the purpose that you intend. So robot operating system, I thought I'd just mention that briefly. ROS can be used widely with mobile robots and some fixed arm robots and cobots such as those from Universal. It's a full software development environment, including a terminal file. I'll turn on the pointer there again so you can see. So terminal here, and then also has a software development kit here, which is really just a file explorer, a coding window, and also then it has a utility that allow and check for your code. Then the top right corner there, it has a visualization tool. I think this is a robotic arm in water because they've brought in some new environments now for sub-aqua and for aqua robotics. So Gazebo is one of the visualization tools, and RViz is another. And ironically, it's not a robot operating system, as the acronym implies, and it's a set of applications, and it does need some familiarity with Python or C++ to use the software development kit. But there is a great training site called The Construct, which provides training on the use and applications for ROS. Yeah, I think if you look really closely here, you'll see my attempts to get ChatGPT and Copilot to get a Turtlebot to solve a maze in the Construct environment. So again, a very useful tool. So just to recap on the steps then, probably the most important ones. Not all tools are needed to develop a business case and the requirements for a robot system, but the minimum are highlighted on this slide here. So walk the line, identify the application, develop a user requirement specification, and then develop a business case, which will need to be shared with your senior management. And then the key thing then is the request for quotation pack that goes out. And often that can include the requirements, user requirements specification. Some of the items that might be mentioned in that user requirement specification are around safety, services, project management, design, manufacture and assembly, pre-delivery tests, the form of delivery, installation, commissioning, final testing and buy-off, standby, training, documentation, warranty, and others. So you can call them out in our user requirement specification, but definitely you should be calling them out in your RFQ pack, in the tender document, or in a performance specification of some sort. But yeah, just to reiterate that the user requirement specification is paramount. So just to summarize, like I would say, just automate the simplest steps first, not the most complex. Automate the processes which are working well already. Not every tool in the toolbox is needed to develop a business case and the requirements. And probably most importantly, talk to a specialist consultant to get agnostic advice. And here's a nice picture of a KUKA robot in a semiconductor wafer fabrication. So I'd just like to acknowledge some of the co-contributors to the guide implementing industrial robots. That was Court Edmondson from the Irish Manufacturing Research, Mike Wilson from the Manufacturing Technology Centre, and then Jeremy Hadall in the Satellite Applications Catapult. So there's a link to that guide. It's on the screen there if you want to use it. There's also a bit.ly link that's down in the bottom corner there. And these will be also in a PDF of these slides that will be shared afterwards. So thanks for sticking with me through the day today of justifying and implementing a robotics application in industry, and now a breakdancing robot.